talk about two concepts called center of gravity and center of buoyancy, and that will help you understand why boats are so safe. So let's talk about center of gravity first. Imagine a pencil, and that pencil, if it was sitting on your hand or if it was sitting on a series of small scales, you'd feel the pencil across your hand. Each one of those small scales would register a little bit of weight because the weight of a pencil is distributed fairly evenly. That can be represented as a center of gravity. If you imagine balancing a pencil on your finger, all of that can be represented, the sum of each one of those little individual arrows, through one arrow pointing down. That can be represented as the center of gravity of a pencil if you're resting it on your finger. So that's concept number one, center of gravity. Now, let's talk about center of buoyancy. So now let's imagine we drop our pencil in some water. The water is pushing up on the pencil, and it does this because the pencil floats. Why does the pencil float? Because the surface area of the pencil displaces an amount of water that weighs less than the pencil, and so therefore the pencil floats. Just about any material can float. It all depends on how much water it displaces and what the weight of the material is. And so just like the center of gravity can be represented around a single point, this one's a little harder to imagine, but if you can imagine like balancing a pencil on the tip of your finger, pushing up, if you could balance it on the tip, that could represent the center of buoyancy. So just like you could take all of the sums of those arrows to represent the center of gravity, same thing, center of buoyancy. So we have those two concepts. If you think about all of the points of where something weighs and all of the points of where something makes it float, being concentrated in one point. And from a physics perspective, that's the way you model things. So now let's take a boat. So imagine this is any boat looking from a stern. So imagine this is like Serenity, as you're looking at the stern of Serenity. So Serenity weighs some amount, and there is a center of gravity. If you had a really strong finger, you could, in theory, balance Serenity on one single point. And that would be the center of gravity. The sum of all of the weight across all of the boat, both side to side and fore to aft, could be measured in one single point. Here, we're really worried about boats tipping is what we're talking about. So we're worried about that center of gravity, left to right, port to starboard, athwart ship, however you want to refer to it. So the side-to-side center of gravity. So there's some point that's directly on center line, and then based on how much the boat weighs at the bottom versus middle versus the top, there's some representation of the center of gravity. Similarly, when you put a boat like Serenity in the water, all of the water that gets displaced, whatever the weight of the water that gets displaced is what the displacement of a boat or the weight of a boat is, and that can be all represented in one point that is someplace below the water line. So it's a representation of the force that the water is exerting to make the boat float, all concentrated in one point. Here again, left to right is the way we're thinking about this. So when you put those two things together, there is a center of gravity pushing down, that's the weight. There's a center of buoyancy pushing up, that is the water pushing against the boat that keeps it afloat. So a boat at rest with nobody on it, nothing moving around, no wind blowing on it, that's what it's going to look like. It's going to be stable and it's going to sit there and float, which is the natural state for not only boats but anything that floats in the water. So now let's talk about what happens if someone was to move around on the boat. So let's say you had some people step to the right side of a boat. Well, what's going to happen to the center of gravity? If the people move to the right side, the center of gravity is going to move to the right side, and the boat is going to tip to the right. Now, those people, relative to the boat, don't weigh very much. If you imagine a paddleboard, if you were standing in the center of a paddleboard and you took just a little step off to the side, well, all of a sudden, that's going to have a big impact. But on a boat that weighs a lot, taking a small step is really not going to have much of an impact on the shift of the center of gravity. But something else interesting happens as well. When the boat tips a little bit, the center of buoyancy also moves, right? So, and this is why boat bottoms are designed like they are, because with this little bit of a V cut, it's technically called a dead rise, when that goes down in the water, the center of buoyancy actually shifts well to the outside. Because again, you have to imagine that the sum of all of the area, if you could find the center of the area of the part of the hull that is underneath the water, that's going to represent the center of buoyancy pushing up. And so boats are designed almost by nature to have the center of buoyancy shift further and faster than the center of gravity does, which basically creates a torque effect. So if you can imagine the blue arrow pushing up, so this arrow is pushing up and this arrow is pushing down, what does that want to do? It wants to turn the boat back towards a normal state, to where the center of gravity and the center of buoyancy are basically offsetting each other, directly opposing each other, which will keep the boat stable. So boats are designed, the shape of the hulls are designed to be able to promote that. If you had something that was flat, like a paddleboard, for example, that center of buoyancy doesn't shift as much, which is why a paddleboard is so unstable. As soon as you get weight on one foot on the side of a paddleboard, there's not an additional amount of water that's being displaced because the bottom of the board is flat, and therefore that's why paddleboards flip so easily. But boats are very different because they have this V-cut, and we'll talk even a little bit more about the concept of ballast. So I know one of the things that I think you were concerned about was the accident that had happened on the 4th of July back in 2012, which was a terrible, terrible situation, obviously. But I read the accident report and have read it multiple times. I read it when it came out and I reread it again. And let's explain what happened on that boat. So imagine we're looking at the stern of that boat. So that boat was a 34-foot Silverton that had a cabin. So this would be much like our boat, like Serenity, but it also has this fly bridge up here on the top. So the investigation found that the weight of the boat was 16,500 pounds empty. So once they got the boat out of the water, first of all, they knew the make and the model of the boat, but the specific boat, they did testing on it. They determined that boat empty would be 16,500 pounds is how much that would weigh. And these are important numbers so you can understand, kind of the relative nature of this. There's some complex math that goes behind this where we could explain the righting moment based on angles. I mean, it gets into fluid mechanics. We're not going to do that, so this is intended to be a simple analysis. Here's what else the investigation found. The investigation found that boat had 27 passengers on it, and those 27 passengers in total weighed 3,519 pounds. It was an average of about 130 pounds per passenger. There were some older folks. There was some adults, a number of kids ranging in ages. On the fly bridge, so up on top, which would be catamount to standing on the roof of Serenity, there were 8 passengers, which weighed 988 pounds on the fly bridge, and there were 7 passengers in the aft deck that weighed 965 pounds. There were passengers then inside, 5 total that were in the cabin, and the remainder were actually up on the bow. So this boat was it was crowded because it's a 34-foot boat. So here's what happened that night leaving Oyster Bay. The investigation found that there was a lot of boats that were leaving. He was running at about half speed, somewhere in the 12 to 15 knot range, and boats, because there was a thunderstorm coming in, I think boats were trying to get by quickly, and so boats had been going by left and right and created a bit of a washing machine situation. And the first thing that happened is because of all those people, the center of gravity is much higher, right? Because people are up on the fly bridge, the center of gravity raises, and the center of buoyancy lowers because it also causes the boat to sit lower on its lines. Whenever you put weight on a boat, it's going to set a little bit lower on its lines. So that was the first thing that happened. The second thing that happened, and this, by the way, makes the boat naturally less stable because in theory, having the center of gravity and center of buoyancy almost at the exact same point would be the most stable kind of boat you could have, which cruise ships are designed to be that way. And we'll talk about that at the end so we can talk about the cruise ship example. But this separated the center of gravity and the center of buoyancy. So with all these boats going by, that created some waves. The accident found that given the way the boat was loaded, that it would have only required a 2-foot wave to get the boat to an unstable situation, which would have caused it to capsize. We see 2-foot waves all the time. I've had Serenity abeam in 15-foot waves. I mean, being in a situation where a boat could capsize in 2-foot waves is crazy, which is why there was just so many people on this. So basically what happened, right, because it was setting lower on its lines, the center of gravity didn't move, the center of buoyancy didn't move as much when this started to tip, so this represents kind of a subtle little wave here, but the center of gravity shifted out to the right, and as soon as this center of gravity, the green arrow, as soon as it got on the outside of the center of buoyancy, you start to have trouble, because now, if you can imagine the pressures working on the boat, this is pushing up, this is pushing down, which makes the boat want to turn even further. And they talked about how they could feel the boat starting to lean, and of course when the boat leans, that actually makes the boat want to turn to the left, because you just the way physics work with something down here, which makes the boat want to tip even more to the right. And then you get in the situation where once it tips just enough, you started to get water coming over the gunnel, over the rail, which they talked about. And multiple of the witnesses talked about how they can start to see the water coming over the rail of the boat. And what that is going to do is shift the center of gravity even further out. Center of buoyancy is still going to remain about the same. And at this point, fait accompli. I mean, it was done. The boat was going to capsize, and it happened very, very quickly.